One of the first things we're going to learn about when talking about energy is the work energy theorem. It is going to explain to us how work done by a force can transfer energy to or from an object. So what is work? Work is energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work. Energy transferred from the object is negative work. So objects have energy and forces can do work to transfer that energy. Our basic relationship for this is that W, the work done by forces, is equal to the change in kinetic energy, and change in physics class is always final minus initial. So delta K is final kinetic energy minus initial kinetic energy. If the net force that's acting on an object is constant, then our relationship for the work is that the work done by the net force is the dot product or scalar product of the net force with the displacement. So the vector D is the displacement of some object. F net is the net force acting on the object. And in general, those two vectors are going to make an angle of phi with respect to one another. And then the mathematical operation that we want is the dot product, which is sort of telling us how much of the net force points along the displacement is one way you can interpret it. So the work done is going to be the magnitude of the net force times the magnitude of the displacement times the cosine of the angle in between those two directions. The direction of the net force, the direction of the displacement. In a bit, we'll learn how to deal with a force that's a variable force. But for right now, let's just get used to the idea of work and deal with a simpler case of a force that remains constant. All right, so some examples of using the work energy theorem. If the net force has a component that points along the direction of the displacement, then the work done is positive, and from the work energy theorem, the kinetic energy is going to increase. If none of the net force points along the displacement, they're at right angles to each other, then the work done is zero, and then kinetic energy can't change. And then last case to consider out of this, if the component of the net force is pointing in the opposite direction as the displacement, then the work done is negative by that net force, and the kinetic energy will decrease. So the object will slow down. This sort of makes sense. If the net force is pointing in the direction of the displacement, it's going to go faster. Kinetic energy increases. If the net force is pointing in the opposite direction of the displacement, then it's going to slow it down. So the kinetic energy decreases. And in between those two cases is the case where the net force and the displacement are perpendicular. So no part of the net force points along the displacement. In that case, there's no change in kinetic energy. All right, so let's try a couple questions to practice this idea, the work energy theorem. So I have a cart on an air track. It's moving at a half meter per second when the air is suddenly turned off. So an air track, think of like an air hockey table, except it's one-dimensional. So we have a cart on this air track moving at a half meter per second. The air is suddenly turned off. The cart is going to come to rest after it skids along for a meter. I repeat the experiment, but now the cart is moving at 1 meter per second when the air is turned off. How far will the cart travel before it comes to rest? So think about what you think the answer is, and then check your answer with your physics neighbor. All right, so the speed is doubling. The mass of the cart doesn't change. The speed doubles, and the kinetic energy goes as a half mv squared. So that means the kinetic energy increases by a factor of 4. Okay. The force of friction doesn't depend upon the speed of the cart. It's the same. So having 4 times the amount of kinetic energy, 4 times the amount of work has to be done. The force of kinetic friction is not going to change, so the displacement has to be 4 times bigger. So if at a half meter per second, it skids for a meter, I double that speed to 1 meter per second, it's going to skid for 4 meters before it comes to rest. We always try to remind students that that square is there in a half mv squared. And that's an important factor you don't want to forget. All right, another work energy theorem example. I have an elevator supported by a single cable, and it descends in a shaft at a constant speed. The only forces acting on the elevator are tension in the cable and the gravitational force. Which one of the following statements is true? The work done by the tension force is 0 joules. Net work done by the two forces is 0 joules. Work done by gravitational force is 0 joules. Magnitude of the work done by the gravitational force is larger than that done by the tension force, or the magnitude of the work done by the tension force is larger than that done by the gravitational force. So think about which of those one statement out of those 5 is true. Which one do you think it is? And then talk it over with your physics neighbor. All right. So the elevator is going at a constant speed. So its kinetic energy is constant. So therefore the work done by the net force has to be 0. The elevator cab is not speeding up and it's not slowing down. It's maintaining a constant kinetic energy. The work done by tension is not 0. In fact, it's going to be negative because the displacement points down, but the tension points up. The work done by the gravitational force is not 0, and it's going to be some positive number because the weight points down, the displacement points down. But the force done by the network is the force done by the work done by gravitational force plus the work done by the tension force, and those two, when I sum them together, will give me 0. If D were true, then the elevator would be speeding up, and if E were true, then the elevator would be slowing down.